it's the closest packed structure, it's the densest you can make in terms of the density of the material that you can pack into a cubic or hexagonal unit cell like this. Okay, so today what I want to do is to tell you a little bit about how to go about figuring out this structure. We've been talking about crystal structure, right? We just introduced the concept of crystal structure. So today what I want to do is to say that, okay, well, how do you know what crystal structure you have? So we're still talking about crystal. We haven't talked about surface yet. We're still talking about this bowl solid that we have. And so I'd like to remind you a couple of things that you can do in terms of wave diffraction. So usually people determine these structure because the crystal are very small, the individual scattering point is very small, and you have something called the diffraction phenomena, and you can diffract any waves. Essentially any waves will have diffraction phenomena. So photon, for example, we have diffraction phenomena. So photon is written at Planck constant times the frequency, right? And of course the frequency is just speed of light divided by the wavelength of the light. So this is easy to understand. So we have also diffraction phenomena from light scattering. So this is just light scattering. So classic example, of course, is X-ray diffraction. You scatter X-ray. We'll talk quickly about this shortly. But in addition to this, just want to point this out. In addition to this, you also have material waves or metal wave scattering. So this is due to quantum mechanics that says that anything, any object can exist as wave form or exist as particle form. So you have a particle like an electron, for example. You can rewrite it into a wave form, into metal wave, so-called metal wave. And this is due to de Broglie, who come up with this idea of metal waves. And so the way you think about this is that your kinetic energy is momentum squared divided by 2m, right? So we know that. And the momentum is given by the de Broglie metal wave. So the de Broglie come up with the idea of momentum is just for Planck's constant divided by lambda, which is the wavelength of your metal waves. So you convert essentially a particle into waves. So you so-called wave-particle duality. You can interpret any matter in this way, either as a wave with a certain wavelength, or as a particle with a certain momentum. So you can think of it like that. And of course, you can then relate, once you know these fundamental equations, you can then relate the kinetic energy itself of the particle, right? E here is the kinetic energy of the particle, to the wavelength of this metal wave. So you can substitute P into here, and what you end up is this, the square root of the energy is proportional to the 1 over lambda, where lambda is the metal waves. Okay? So why I want to talk about this is because it's very powerful. This de Broglie metal wave is very powerful because you can, when you want diffraction phenomena to occur, your scattering point spacing must be very close to the wave that you're going to scatter about. So you send in a light wave, your crystal structure is typically between atoms. They are typically measured in terms of angstrom, right? That's why we have unit angstrom, 10 to the minus 10 meter. And so if you have a wavelength very close to that, then you would have diffraction phenomena. Okay? So what you're trying to do is to create a wave situation that's very close to an angstrom. So let's think about that. So let's first look at X-ray scattering. So you send in X-ray photon. So it's a X-ray, and what energy do you need? So for example, if you calculate the energy of the photon using this formula, this is for light, right? So you just Planck's constant times speed speed of light divided by lambda. So this two constant is 12,400, very useful number to remember. If this is in electron volt, then 12,400 divided by lambda, and lambda is in Armstrong. And if you calculate what this energy should be, assuming that lambda is 1 Armstrong, right? So E for where your lambda equal 1 Armstrong, that's what this notation means. So here we say lambda equal 1 Armstrong, like this, right? And what is the energy that you have? You have about 12.4 kilovolt, okay? So if you have a X-ray light source of about 12.4 kilovolts, then you should expect diffraction phenomena. So if you, some of you may have know about powder diffraction. The chemistry department has powder diffractions, and what they have in their X-ray light source is copper source, and copper has a energy about 40 kilovolts, about 40 kilovolts. So it's very close to this 1 Armstrong limit. 40 kilovolts could give you about 1.5 Armstrong, and so what you have then is very close, very good match for diffraction phenomena. That's why people love to have some sort of copper source, because they are very close to between 1 to 2 Armstrong. Okay, so usually when you talk about X-ray, hard X-ray meaning that above 5 kilovolt, that's hard. Anything below 5 kilovolt, soft X-ray. Then you're talking about tens of kilos of electron volt in the X-ray photon energy that you have. Okay, so that's why you see all this copper tube, X-ray tube, is because it generates a lambda between 1 to 2 Armstrong to allow you to have diffraction phenomena. Okay, so that's photon diffraction, light diffraction. Now, what about matter wave diffraction? Now, another very popular thing that people do, less popular now, but in the old days it's quite popular, is neutron scattering. So you have a neutron beam created by some high energy physics facility, and then you scatter this beam onto your material, and that has been used quite a lot about neutron scattering. And how does that work? Well, neutron scattering really is also like X-rays diffraction, really, because if you look at the neutron, in this case, you are going to use this formula because neutron has a mass, and you calculate what kind of neutron energy do I need in order to scatter, to create about 1 Armstrong wavelength, so that you have diffraction phenomena. So you punch in the appropriate number. So here you're changing the mass of the neutron. You're using the mass of the neutron in this expression here, and you end up with you got about 0.28 or so. And so in order to do that, what you have is that you need only a very slow moving neutron beam. It's about less than 1 volt, very less than 1 volt, less than 1/10 of a volt. In fact, it's only 80 millivolt neutron beam. If you can create an 80 millivolt neutron beam, you would have a matter wave roughly about 1 Armstrong, and that is very nice for probing the material. That's why people use neutron scattering to find out the structure of your bulk material. Now, for surfaces, people have used electron diffraction, and so you do the same thing. You put in the mass of the electron into here, and you calculate what this factor is, and it turns out to be